When your pocket calculator displays the sine or cosine of 45 degrees, the result is only an approximation. To find the exact value, apply the Pythagorean theorem to this right triangle. The hypotenuse has length square root of 2. Divide the triangle in half, and we find the sine of 45 degrees is 1/2 the square root of 2. So is the cosine. Sines and cosines of many special angles can be found exactly. For example, in this equilateral triangle, each angle is 60 degrees. Divide the triangle in half to find the sine of 30 degrees, which is also the cosine of 60 degrees. Use the Pythagorean theorem to calculate the length of this leg. Then we find the sine of 60 degrees, which is also the cosine of 30 degrees. The addition formula enables us to use the sine and cosine of two angles to find the sine of their sum. For example, using the sine and cosine of 30 degrees and 45 degrees, we can find the sine of their sum. Which is 75 degrees. And the subtraction formula gives us the sine of 15 degrees. These are also the cosines of the complementary angles. All these are exact values expressed in terms of square roots of whole numbers. To find more sines and cosines, we start with this regular pentagon. It has 5 diagonals of equal length. They form this star-shaped figure called a pentagram, an ancient Greek symbol of health. These 5 equal central angles fill the circle, so each is 1/5 of 360 degrees. This inscribed angle is half the central angle, or 36 degrees. The base angle of this triangle is also half its central angle, or 72 degrees. If these two equal sides have length 1, what is the length of the base? We can find it with the help of Ptolemies Theorem. The product of the lengths of these two opposite sides plus the product of the lengths of these two opposite sides is equal to the product of the lengths of the two diagonals. We get a quadratic equation for x. It has two solutions, one negative and one positive. We want the positive solution. The length of the base is the square root of 5 minus 1 divided by 2. The Greeks called the ratio of these two lengths the golden ratio. We'll see it again in a later program. Now we can find the sine of 18 degrees, which is also the cosine of 72 degrees. And we use the Pythagorean theorem to find the sine of 72 degrees, which is also the cosine of 18 degrees. Because we know the sine and cosine of 15 degrees and 18 degrees, the subtraction formulas give us the sine and cosine of 3 degrees. Then by repeated use of the addition formulas, we can find the sine and cosine of 6 degrees, 9 degrees, 12 degrees, and all integer multiples of 3 degrees.